Hello and welcome to another episode of Twiml Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. The show you're about to hear is part of a series of shows recorded in San Francisco at the Artificial Intelligence Conference, which was hosted by our friends at O'Reilly and Intel Nirvana. In addition to their support for the event itself, Intel Nirvana is also our sponsor for this series of podcasts from the event. A huge thanks to them for their continued support of this show. Make sure you check out my interview with Naveen Rao, VP and GM of Intel's AI Products Group, and Scott Apland, Director of Intel's Developer Network, which you can find at twimlai.com/talk/51. At the AI conference, Intel Nirvana announced DevCloud, a cloud-hosted hardware and software platform for learning, sandboxing, and accelerating the development of AI solutions. The DevCloud will be available to 200,000 developers, researchers, academics, and startups via the Intel Nirvana AI Academy this month. For more information on the DevCloud or the AI Academy, visit intelnirvana.com/devcloud. Our first multi-person interview. I speak with Mo Patel, Practice Director of AI and Deep Learning, and Laura Frølich, Data Scientist of Think Big Analytics. Mo and Laura joined me at the AI conference after their session on training vision models with public transportation datasets. We talked about this and a bunch of other interesting use cases they've worked on involving image analysis and deep learning, including an assisted driving system. We also talked through the practical challenges faced when working on real machine learning problems like feature detection, data augmentation, and training data. All right, everyone, I am here at the AI conference, and I am with a couple of guests this time. I am with Laura Frølich and Mo Patel with Think Big Analytics. In fact, Mo and I, we had an opportunity to meet at a conference a while back, and you kind of came up to me and introduced yourself as a listener of the podcast, which I think that was maybe the first time that ever happened to me, and I was like excited out of my mind. And
I remember you were actually talking to the people at Chainer, the deep learning framework, and I was like, I recognize that voice, and that it's funny, it's a very recognizable voice, yeah.
Yeah, and we had an interesting conversation about the industrial AI stuff that I was working on at the time and some of the work that you were doing there. So then when we saw that you and Laura were doing a presentation here at this conference in San Francisco, I thought, we got to get you on the show. So welcome.
Thank you.
This is actually the first time I'm doing an interview with two guests. So it'll be interesting to just how the kind of traffic management works. But why don't we start by having Laura, you introduce yourself.
Okay, so currently I'm a data scientist working with Think Big Analytics, as you just mentioned. So I work on all types of projects. Like whenever a customer or company has a lot of data that they want to gain insight from to solve some use case, I can help them out. It doesn't have to be deep learning, like any sort of method that tries to reveal relevant patterns using some method that makes sense given the use case and the data at hand. We'll go with that. Before joining Think Big, I spent half a year in a research group where they investigated something called non-specific effects of vaccines, which is basically vaccines turn out to affect the immune system in a general way, not just protecting against the targeted disease. Okay. So very interesting research. Prior to that, I did a PhD at the Technical University of Denmark using various machine learning techniques to analyze brain activity data.
Oh, wow.
Yeah. So that's sort of my background.
Okay. And Mo?
Yeah, I'm currently the practice director for AI with Think Big Analytics, mostly looking at America's customers. And part of that is probably not as working on projects as much, but doing more of the proof of concept type work. So taking some of the most advanced things that are going out there and see if we can apply them to our clients' problems. So part of that, so there's a hands-on portion of it, but then there's also the dreaded like PowerPointing of things, kind of conversion of like that, like the highly technical stuff into things that people understand, which is a kind of a fascinating part of it, because I really love that, trying to lower the barriers to, because there's a lot of hype around AI, trying to lower the barriers so that people can understand that this is not Terminator, it's actually just math, right? And so that's kind of my day to day. I really like doing that, and my background is, I come from, if you look at like data science, AI, machine learning type things, I come from more of the computer science side compared to like people who come from statistics or maybe from some sciences, the hard sciences. Over the years, software engineering into transitioning into more math type software engineering, and then into analytics and yeah.
Oh, nice, nice. And so the two of you did a talk yesterday. It was actually a tutorial?
Yeah.
What was the tutorial about?
The tutorial yesterday was on image analysis using deep learning methods, in brief. So we had both a general introduction, making sure that everyone was on the same level. Everyone agreed on what is an image, what are pixels, what sorts of values are we dealing with, and so on and so forth. And also going into what sorts of problems can we talk about in image analysis. And then we went into more detail on one particular topic, object detection, and zoomed back out a bit in the end. So that's how I sort of see the whole framing of the talk. I don't know if you have anything to...
Yeah, no, absolutely. I think just kind of making sure that people are aware of the computer vision basics, and then diving into something that is fairly cutting edge, object detection, and a lot of applications out there, and not only the theoretical part, but also in a notebook style kind of layout, saying, hey, this is how you can actually do it yourself as well, right? Felt that was very compelling. And then towards the end, talked about some of the challenges around training models. It's like we make it sound so easy, but to do it for real data, there are many challenges, and so we talked about that, and we can go into that detail if you want.
Yeah, what are some of the challenges?
So absolutely. For example, there was a paper that came out over the weekend, how this team trained the ImageNet data set in 24 minutes, right? And when you look, a little
bit of a controversy.
Yeah, it was, of course, because it's like, well, they used that headline was AlexNet, not ResNet, which is like more of the current state of the art, and then what kind of hardware you use, and all sorts of different things. But that is exactly the type of thing, right? Is that what are all the different parameters like batch sizes and different processors and multi GPU, multi server? Because most of the things you see, the examples of tutorials, it's like, just run this code, right? But if you're in production, when you have like a million images and you need to make sure that this will train over like days and not weeks, you may have to scale it. And how do you do the scaling? And those are all the challenges. That's kind of like more engineering style challenges, but then there's also challenges around annotation, right? It's like, well, this is supervised learning. You have to annotate the data, and that could mean anything from it's like simple classification, kind of easy, so to speak, right? Where there's a picture and there's a label, right? Now for object detection, there could be bounding boxes, so you draw squares around the objects, like around balls and like umbrella and things like that, to make sure, and then label it that this is what the object is. And then even something more advanced, which is kind of drawing the polygons around the object itself, which is the segmentation, kind of like the holy grail of getting towards being able to do object detection. Many challenges, and of course you can try to do it internally or externally. We actually, for our project, we actually built a segmentation tool that allowed people to go ahead and draw boxes around cars and pedestrians and things like that. So, as much as we talk about the deep learning parts, right, there's all sorts of many data engineering, data prep, data cleaning, things that have been around also in the traditional data science for a while, right? So very much of a challenge.
And to add to that a bit, with the annotation tool that we built internally, we have that tool and we were using it internally, but our team was just not large enough to annotate enough images quickly enough. So we had to both use that and go to an external company to get help from them to annotate all the images. And there was a lot of back and forth with them just defining their requirements. What sorts of things do we want labeled? How do we want them labeled? Like, what's the smallest size of object that we require labels on? What do we do if it's partially obscured? Like if there's a car blocking another car? those sorts of things, because you may have difficulties if you have a really small object and you label it. Then during the training phase, you'll be punished. The model will be punished if you don't detect that object. But it may actually not be very interesting to detect that object at test time, because small objects are far away. So you may want to focus on objects that are closer. So one way to handle that would be to put an extra label on small objects saying difficult. In that way, you might handle such objects differently from normally labeled objects by not punishing the model if it doesn't detect them, but also not punishing the model if it does detect them.
Yeah, I've had some interesting conversations with folks that specialize in labeling data for folks, and it really opened my eyes to just this process that you're describing. Like, you think of, hey, just label my data, but if you're talking about images, there's all different kinds of ways that you can do it. And they have direct impact on the types of, not just the types of models that you're creating and their performance, but the cost of the labeling process.
Yeah, exactly. So this company that we worked with had this quite elaborate pricing scheme. I never really looked at the details of it, but if you increase the number of classes, you would sort of get an extra cost to the first classes as well. Okay. So you really had to consider, or maybe can we sort of have this external company do part of the labeling and then do some further post-processing in our own tool.
You needed a machine learning model to optimize the pricing for the vendor tool.
Yeah, exactly.
And there are some interesting projects around that. There's that Snorkel project from the Dawn Lab at Stanford. They're trying to do some stuff around kind of around the training data and building more training data. Which just reminded me, another big one is data augmentation, which is another thing that if your data doesn't have, an example I gave is that having the road data for when it's foggy versus when it's not, right? And what if we never capture the fog based, which would be hard to do in San Francisco, but so those are all the type of things that, so luckily, at least what's great is that much of this knowledge has been encoded now, where they're just in Keras, there's just a function for data augmentation. Sure, maybe you could add your own, but there is that state of the art, might as well just use that for when you're in your training process. But these are all the things, and it's when you think about simply, it's just take the images, run it through a deep learning model, and out comes your trained model after you do all the deep learning things like generalization and loss optimization, all those things. But then there's all these other things that you have to kind of worry about. Yeah.
And regarding data augmentation, even though people have made tools that you can sort of just use, you of course have to think about all of the data augmentation steps. Do they make sense? For traffic scenes, do you really want to flip your images horizontally to teach the model that an upside down car is also a car? Well, maybe you do, but it depends on your use case, right?
Right, that would depend on your use case.
Yeah.
I mentioned the action movies, you may want to get those upside down cars, yeah.
And so these are just some of the issues that you run into in the training phase of building and deploying a deep learning model. And then there's the whole, how do you actually get this out into the wild to do inference? Are there, best practices, tips, tools of the trade, or, tricks that you've come across for that?
Yeah, actually, as much knowledge there's out there about the training aspects of it, there's actually not as much. And something that, even traditional machine learning in production, I think we heard this thing about data science that there's not there's a lot of talk about it, but in production it's still not, you could do a survey and you could probably find that only maybe of all the people who actually say they do data science, only 25 to 30% maybe actually putting into production. And then once you get to deep learning, that number could start even going lower. And I think that's just because, as you were saying, that there's a whole different set of challenges when you're trying to put models into production, right? So number one, where are you going to put it? Are you going to put it on some beefy servers in a data center? Right. Then maybe you have lesser problems because you could take those big gigabyte-sized models and distribute them across containers and kind of a lot of the traditional way web apps are served. But then you start talking about, well, we're going to do mobile. Well, that's that becomes another challenge. How do you compress the models? Maybe quantization, lowering the floating point and things like that. So that's another. And somebody actually asked this question. They're like, "Oh, so can I take this and put it into a car to do this?" And we are like, "There's a lot more that will go into it before you be able to do that." So the training is definitely challenging. but being able to serve the models at scale brings in kind of all your traditional DevOps and data ops, kind of bring it all in. Model management, version control of the models, and data lineage, traceability. Everything that we've been discussing for any other data science type things, those are all they're back on the table, right? And how complex those can be.
Are there emerging or accepted tools or open source projects for doing that kind of thing? I know that, some of the vendors that focus on, machine learning platforms, they've got some of that stuff built in or integrated into their tool set, but it's all like, within that tool set. Is there a kind of an open source model management framework, for example, that's kind of emerging as a standard, or does it have to be kind of custom cut for an individual use case?
At least I haven't come across. I know we built one internally. Yeah, from just a lot of our projects, right? Because we saw this need of model management, and it's internally called Think Deep, for managing models. It's maybe it will become open source. You know how these things go. At Think Big, we have tried to make things open source. For example, the Kylo framework for data lakes. So this could be another path on that roadmap. But there's a lot of polishing that needs to be done before it gets. So
folks should reach out to you if they want to get their hands on this open source model management.
Possibly. I'm not the developer on it, so I can definitely put in touch. But I have not come across. There are definitely some projects. Once again, the formerly AmpLab, the UCB Rise now, right, and then at Stanford Dawn, right. They have, I can't remember the names of the projects off my top of my head, but I've seen that's in their program agenda for being able to serve large scale machine learning models, and you could consider deep learning into that. And I will, I'm not to do a commercial plug, but that's actually one of the things that we are also focused on, because when we look at things, it's like, yeah, training is there, but we work with traditional customers, enterprise customers who want to put all that stuff into production, because all the investment they make on AI or deep learning, data science is useless unless they actually put the models into production, right? So building the tooling around that, monitoring the models, and all of those things are interpretability is a huge part. All of those, being able to kind of have a one-stop shop for that is very attractive. Mm-hmm. Yeah. So there's commercial aspects to it.
Interesting. So before we got started, we mentioned a few use cases that you would be able to kind of talk to us about and walk us through. And the first one is one that you worked on, Laura, as a traffic project that you worked on with an automotive parts manufacturer. And it sounds like this was in some ways an inspiration for the tutorial that you did here. Can you tell us about that one? Very
much. So this project was for an assisted driving system. Okay. So not self-driving at all. We didn't want to go there, but just to help cars help each other, essentially. So the idea was that you have a car that's connected to the system, and it's driving along, like doing whatever it's doing, going where it's going, and it has a camera recording whatever it passes. If it happens to pass a stopped car that's on the road, it might be a good thing to be able to detect that, to tell other cars, hey, look out, if you're in this lane, you might want to change lanes already now, so you don't sort of get a surprise when you get to that stopped car. Mm-hmm. You could even have that indicate there's an accident or just congestion. Mm-hmm. So stopped cars on the road is definitely something that you might want to tell other cars about. Right. So the project was about trying to detect this, and there are a lot of steps to this. First, a video is, of course, a lot of images that come in one at a time. So the first step was trying to look at, okay, so how well can we detect the objects? Okay. And trying to compare the various object detection methods that were out there, see how fast are they, how accurate are they, all of these things, and also try to get an idea of how might we be able to improve them. Then subsequently, you have to be able to tell, is this part of the picture part of the road, or is it not part of the road? Because if it's not part of the road, if it's a parking lot, you don't care so much whether there are stopped cars in there. So that's another thing. Thirdly, you'll want to be able to tell, is the car moving? So one thing is detecting the cars in each image. Another thing is seeing, so this is the same car that I just saw in the previous image. Right. And then estimating the distance, the difference in distance from when you saw it last, trying to estimate its speed. Okay. So this comes into object tracking, which is seemed to, from the research that we were able to do, to be still quite immature compared to object detection.
Okay.
So for object detection, there are already a lot of methods, a lot of research out there. For object tracking, it seemed to be less solved. Okay. So we spent some time looking into that. And so in the end, we had a demo that was able to detect most cars and sort of give an estimate of, is it moving, how fast is it moving? Mm-hmm. And that was basically where we stopped.
Okay. And were you exclusively trying to detect cars or other obstacles in the road?
So we did want to detect other objects in the start of the project as well. Uh-huh. Turned out that there were some difficulties with that because in traffic datasets, you tend to have a lot of cars, right? You don't have as many people. Uh-huh. You don't have as many bikes. You don't have as many buses. Right. So your training data has a high imbalance. Okay. And that just makes it more difficult to learn those other classes that are not cars. Interesting. So in the end, we ended up focusing more on just the car part of it, okay, and not so much on detecting all the other classes that we were initially interested in.
Okay. Oh, interesting. So you mentioned the object detection methods that you came across. Can you kind of summarize the state of object detection and what are the main methods and what you found as you compared them one to the other?
So the methods that we looked into most were the ones that were quite recent at the time of the project, which was like in the beginning of this year. Okay. So at that time, there were a lot of what's referred to as single-shot methods. So you have two versions of one called You Only Look Once, mm-hmm, YOLO. There's one called single-shot multi-box detector. Okay. And what these methods have in common is that they just look at the image once. Mm-hmm. So you'll take the image that you're trying to analyze and pass it through the model once to extract features. And then based on those features, you'll predict the coordinates of the bounding box as well as the class of the object within the bounding box. Okay. And you'll do that for a bunch of predefined boxes on the image. So before seeing the image, you'll already have defined a large number of what's called prior boxes or default boxes. They have various names. Mm-hmm. So for one particular method, it's around 7,300 prior boxes. Mm-hmm. For each of these boxes, you give a prediction of the class that it might contain and a correction to the predefined coordinates to match the object better. Okay. And that's sort of the general theme for these single-shot methods.
Okay. Is that they'll predefine some large set of boxes and then detect objects relative to those boxes?
Yeah, exactly.
Okay. Interesting. And then on the object tracking side, what was the method that you found and what was your experience with it? How did it perform?
So we ended up using a heuristic approach. So basically looking at the detected objects in a number of frames. I think we ended up with around looking back at the past 20 frames, basically trying to match the current car that we're looking at to the car in the previous images that matches the color the best and has the closest Euclidean distance and those sorts of heuristics. Okay. And that turned out to work pretty well. Okay.
And you mentioned kind of doing a scan of the literature. Was that one of the methods that you found in the research, or were you not able to get any of that stuff to work well?
Yeah, exactly. So the methods that we found and tried out, we spent quite a while trying to get them to work, and it didn't really work out. So in the end, we just thought, okay, let's try heuristically, see how it works. Mm-hmm. And it ended up working pretty well. So then, in the interest of time, we went with that. And of course, we're hoping to get some of the more advanced methods to work in the future. But the heuristic approach turned out to really give quite good results.
Which is also an important lesson for folks that actually have problems to solve.
Yeah. And, it's like I was observing that project mostly. And of course, as you were just saying, right, it's like for an outsider, I was like, oh, this is clearly, you need to use you're using convolutional networks, but then use recurrent on top of that because you're trying to track, something and then maybe do the predictions for future frames and things of that sort, right? And that was the kind of the common, and actually, of course, that's what I searched for, right? And there is somebody who is working on a recurrent YOLO.
We did try that actually. That was one of the things we tried.
It didn't work. And that's what we mean, that maybe, this is something that will, as more people experiment and it will start evolving, and because object tracking is another great area for computer vision.
That's a big challenge for folks that are implementing this stuff, like in real use cases, is that, I've heard it described and I've repeated it as kind of overfitting on a data set, right? Like, hey, this works great for ImageNet, right? But, for another data set, it's hard to reproduce the results.
And that's actually another issue that we ran into. So we took this pre-trained model that someone had on their GitHub repo just to see how it worked, and it didn't detect anything. So this was a segmentation model, and we wanted it to detect roads, and it just didn't detect anything. And of course, in our images, we had a lot of roads because this was a traffic data set. So we were like, why is this? And one of the team members wrote the author, and he was like, oh, well, that's because I didn't do data augmentation, because I wanted to improve the performance as much as possible to the data set that I'm submitting this entry to. Right. So this was a competition, and he was just optimizing to these lighting conditions and so on that the data set had. So when we retrained the model with data augmentation, it was actually able to detect a lot more road. Even we didn't add any data, we just used data augmentation.
And what is data augmentation doing in this process?
So I think some of the parameters that we tuned in this case was adjusting the brightness of the training images. So like we had the original training images that this guy had trained on, but then we added the same images but with different levels of brightness and other things to the training set.
So essentially to deal with things like glare, nighttime, twilight, and all sorts of other lighting type situations, right?
So you just do a bunch of different transformations on the image to, adjust the brightness by a few minus a few stops, or maybe apply some cool Instagram filters.
There you go. Well, actually, it's what's great. Once again, I love this field, right, and everything people are doing, because there is a paper around this topic of data augmentation and best practices, and much of has been codified in Keras and some of the other computer vision libraries. So you don't have to do imagination. It's like, let's just apply this best in class data augmentation, and then we will just see if it works. Of course, if it doesn't, then you may have to go inside and tweak some things. Yeah.
Okay. Awesome. Anything else on that project?
Not that I can think of right now.
Yeah, I think another thing from just my observations was that international, it's like everybody has their local perspective, right? And we have kind of a US-centric viewpoint on traffic and driving. And I think there's just a different set of things in countries, right? And one good example of that is traffic signs, right? Is like a stop sign is, the concept is somewhat universal, but it is different in other countries. Right. So these are the type of things that you have to account for if you're trying to do more like sign detection or other types of things.
Mm-hmm. Right? Yeah. Excellent. So you mentioned a project called Lost and Found that was for a logistics company?
Yeah. And that one, as much as this kind of object detection type things, that one had a little bit of a different type of challenge, and that is that type of thing that we're trying to find, right? So it's like, imagine you're shipping packages and then, somehow the package loses its tracking, label rips off or box break. And then, so this company finds the item, and now it's like, okay, what is this? Because a lot of times it's not really clearly. Or you as a customer will call and say, I'm missing a brown pair of shoes, with this and this, and somebody's manually going through all the stuff to find it, right? It's a very tedious process. And so how do you build a system that could give you based on some description? And I know Google Image Search does this great, but we don't have, it's not available as an API even, Google's not giving it to everybody. And so there are some cloud APIs, but still not this. The point I'm trying to make is that the universe of items you could lose is infinite, right? It's not like 10 class, 90 class, 9,000 class. It's like infinite. So doing an object detection model that will say, oh, we'll just detect the label of the item and we'll just be able to find it. So the approach was a little bit of a combination of transfer learning and feature matching, as opposed to feature engineering, feature learning. So, one thing that customers do when they ask the question is they actually could provide a photo from the internet, or they may actually have the item. And, this all sounds like probably somewhat easy for commercial items, right? But if you think about industrial items or niche things or collectibles and stuff like that, that's where you really start getting into the problems finding these items.
Well, certainly you're not going to have them just sitting around in your training data.
Yeah. The way to kind of tackle this problem is like an image search problem, right? And previous generation techniques were doing, a lot of the handcrafted features. There were algorithms like SIFT, SURF, and ORB, and some of these previous generation feature detection algorithms, I believe.
If you open SIFT, SURF?
Yeah, SIFT, SURF, and ORB. These are all acronyms for feature detection in previous generation computer vision. Matter of fact, I think, and of course I don't know the details, but when I look at it, the Amazon app, when you open up the visual search, I think they're not using deep learning. They're using that previous generation because of the dots it's showing. And based on just my knowledge, that's exactly how it works. So I don't know if maybe somebody from Amazon can verify, or maybe not. They probably don't want to. But yeah, so we were like, well, we don't those. One of them, I forget which one, is actually proprietary, so we can't use it, without getting a license, and all sorts of challenges like that. And we have deep learning now, so being able to extract using some of the state of the art models such as ResNet or Inception, and just really thinking about this problem. It's like, well, what are those models doing? Right? You have high dimensional data, images, and the point of generalization is to come up with low-level features that you can generalize so that it will work on not just that data and on a much wider data. So, well, why don't we just try to take our target and the source and essentially extract those low-level features and create a feature store, right? So the next time you have to search for something, you say, okay, it's almost like fingerprint matching type. That's one way to think about it, right? It's like creating the fingerprint of the search, and then we have the entire database of fingerprints, and you just say, okay, find the one that's the closest match. And we didn't have to get it 100% right, because there was a human in the loop that somebody would say, okay, all right, I can tell between these 5 images that this is the one, right?
Did you define your features a priori, or did the training process?
Yeah, we just used it. We didn't do any training. We just used a pre-trained model, for example, ResNet or Inception. We removed some of the classification layers because we weren't interested in the classification, right? Because if you look at the deep learning model, that's what the lower layers are doing. It's eventually, after the features you get to the low level, you then do your classic classification, and then so we said we're not interested in that. Let's freeze the model at a certain level, and then see what the features are coming out of that. Store those, and then let's do the same thing for the search candidate. And then the object tracking, there's a lot of similarities as far as the Euclidean distance type thing, where you're trying to make sure that it's the same car from the previous image to this image. Right. And then, so once you extract the features, you try to do a distance and see how closely they match. Mm-hmm. And that's essentially what you're trying to do is that in this case, we were doing a cosine distance between the both of the feature vectors, or the kind of the customer's feature vector, and then the entire database of images, objects that we have, to find the closest ones. So that's kind of like, in a nutshell, that's how that problem was solved.
On that one, did you determine where you were going to freeze your network based on experimentation, or was it more kind of intuitive, this is where the classification starts, so we're just going to stop here?
So yeah, if you ever kind of dissect one of these models, you can read all the layers, and yeah, you can tell which layers is when the kind of the feature extraction stops and the classification starts, typically around kind of densely connecting and softmax classifier. Those are kind of the later stages. So once you stop your convolution layers, that's when you can stop. And yeah, we try to experiment with like till the very end or somewhere in the middle, because these models are also the state of the art, have 50 layers, like many layers. So it's like how, because we were not really interested in doing the classification. So at what level of raw features that our search works at a good performance? Yeah, right. Because once again, like if you get to like really low level, then our search results will be like all over the place, right? Yeah. So we want to capture at some good level. So they're not a scientific way. It's very much was a trial and error to come up with where it was giving us the best results.
So I was actually wondering, just Now, did you use features from many layers at once, or did you pick just one layer and take the features from that?
Yeah, after several layers, so like 25 or 30 layers, we said, okay, now let's see what the output of the image is, the feature vector, and said, no, this is the one we want to use.
Yeah, I'm thinking inspired by these object detection methods that tend to use features from different layers to capture both large and small objects in the image. But I guess it's not so important if you know that you have one object in the image and you're just trying to find that one object, right?
Yeah, typically so what I didn't mention is that this company, when they get the item, they take photos of it, right? Multiple angles and everything. So typically that's the only thing that's in there. Once again, all classic problems still are there, like data cleaning and background removal and all sorts of things like that.
Yeah. Interesting. And you mentioned one more, which was a fraud detection app for a bank.
Yeah, and did you want to talk about it? I can also talk about it,
If you could start to talk.
Yeah.
So I wasn't on the project.
Okay.
I know about the project, but
yeah. I just felt like because it's in Denmark, right? Is this? I think more details can be found because the video of this project. There was a talk at the O'Reilly AI conference in New York in June, and it's available online. So those who are interested into this technique, I think what's really neat about this is that in the previous two cases, we talked about computer vision, right? Which is kind of the cool factor, right? Because everybody is excited about being able to do things with images, right? But now here comes like fraud detection, which is, to the common person, it's like, who cares, right? As long as my credit card works and nobody defrauds me. But banks, of course, are very much concerned with that, right? So in this case, we were like, well, so of course, fraud detection is not new, right? People have been doing this for decades, all sorts of things like human curated rules, right? It's like you swipe a card in San Francisco and then you swipe it in, Bombay or Mumbai, right? It's like, obviously there is a problem, right? And so it's, things like that. You can always have those handcrafted rules, but those can become like, you have 20,000 rules, and it's like, becomes a real cumbersome process. You start applying some traditional machine learning aspects to it. So you do a lot of feature engineering on the data to say, okay, these are the features that contribute to fraud, and we should flag for that, right? And then we are like, well, what are the ways you can improve upon this? Now we have deep learning, feature learning. Are there ways to actually improve upon the model? And so we said, well, let's try a couple of things. So one of the things, and this is a classic like the object tracking example as well. Like, so it's like, well, what is the first thing I would do? And well, most people with transactional data or sequential data, the go-to technique is using some kind of a recurrent model, right? Where LSTM or something like that, right? So that you have the recent history, and then you should be able to tell, oh, this is fraudulent, or it's about to be fraudulent. So we tried that, and actually the model result, if I recall correctly, there's a chart in that talk which shows you all the different approaches. I think it was on par with the traditional machine learning, so not really, it's not promising. But then it's like, well, a creative way of like, well, what if we could apply some of the vision-based techniques? So it's, vision, there are certain properties that are necessary for a convolutional model to work. Shift invariant statistics and locally correlated values. Those are the two things that famously Jan LeCun tweeted out a few months ago, which I remember very well, right? I'm not having come from research, right? And those things really made a lot of sense to me. It's like, okay, all right, so those are the properties you need, because traditionally the type of data we have, even in credit card transaction, is just some kind of a time series. You have amount and location and all sorts of things like that, but not like a picture, right? And this technique is detailed in if even 5 minutes of that talk, there is a couple of slides on it, which will just like visually, it's very intuitive, is to come up with a feature map of the transactions using some history. So then the idea is to create like a visual image of the recent transactions and then feed it through the convolutional neural network to see if you could detect fraud. When you think about this, and this is something that I would ponder others to think about, right, is that think about this as how we would do something like that, right? And one example I always talk about is that people who sit in like operations controls, right, and they're looking at those 50 screens, right, or even traders when they look at like all these charts and all these things, right, they're visually also trying to look for some changes in signals that will allow, say, oh, I need to take some action. And the idea is very similar here, right? Is that if we could convert, I mean, there's data behind those charts, right? If we could somehow create we just like, we'll create charts out of the data and then feed it through the convolutional neural network and then tell it what abnormal looks like, right? And then now ask it to flag it. So
it's super interesting. I think those traders would be a lot less effective if they were looking at a spreadsheet.
Yeah, well, we know that, right? It's like it's like imagine if I gave you like a trend chart versus like all the data in a table, right? How quickly could you make a decision, right? And
so put like that, it's super intuitive that a neural net would, a vision-focused neural net would be effective in solving these kinds of problems.
Yeah, and it's a great. I love talking about this because it's a great example of applying some of these kind of what the research there and the progress that we are making in computer vision towards a problem that you wouldn't think is in that realm, right? And you can talk about, I mean, and when you start thinking about this way, there are many more things that open up, like, anomaly detection and anything that you can visualize, like if you have like a heat map, right? So yeah, sure, we can generate a heat map of a lot of data, right? I think the big trick over there is that you have to be consistent in the way you feed the data, because remember the properties of the convolutional neural networks require that. It's like, think of it, it is an image. If you start shifting around the bits, the image will stop making sense, right? And that's what we are really banking on, that there's an image that makes sense to us, and we are trying to find those patterns. So it is very important that you don't use another technique the next time around. You keep the feature map same for even throughout the production cycle, right? Not change it around, not change the sequence of transactions and things like that.
Okay.
Yeah, it's detailed much more in that talk if anybody's interested.
We'll try to track down a link to that.
Yeah.
Awesome. Well, these are all really, really interesting use cases. Thank you both for taking the time to kind of talk through them. Is there anything else that you wanted to mention? Either of you?
Nothing comes to mind right now. Probably something will in like half an hour.
Yeah, of course.
I'll take Sam's role and I'll ask you, what has your impression been in this, I guess, day or half so far at the conference?
Well, I have enjoyed it personally. I think there are a lot of really interesting talks and some that I would have liked to go to, but that were just filled up by the time I got there. Oh, wow. Like there was one on what to do if you don't have a lot of data, because there are some ways around that, I gather, and something that a lot of people are starting to talk about as well is the use of unsupervised learning. Mm-hmm. I don't remember the details, but I ran into this really interesting paper where they started, so they wanted to train some kind of image analysis, object detection, something method. I don't recall the details. The insight that they had was that, well, how do children learn to associate shapes that sort of belong together? So if a child sees a cat the first time, it may not know that the legs and the head and sort of everything goes together into being a cat. But then when the child sees the cat move a lot, it sort of realizes, okay, so this is a cat and these parts belong together. So this is one object. So this is essentially learning how to detect a whole object. And there is some research that shows that this is indeed how children learn to recognize shapes, or people who regain sight, or like that. There is actually some research showing that this is how it might work for humans. Mm-hmm. So based on that insight, what these authors did was just show videos to a deep learning model, and it did learn to recognize objects in this way. Oh, wow. And then once it learned how to recognize objects, then it's easier for it to learn that, okay, so this object is a cat, this object is a house. So,
interesting.
So I thought that was a really cool application of using unsupervised learning to gain momentum.
Yeah. Oh wow! Yeah, like a little bit of a roundabout way of going around the labeling aspect. Yeah, it's pretty neat, and I think that's it's great. Some of these research moving forward around, it's because we've been talking about big data related, machine learning, right, with deep learning, but there is a lot of data class imbalance is a huge thing, right? Just that there's some places where there's just not enough things to detect. How do you handle those things? Yeah, so it's very fascinating, and I'll say that for me today it was really fascinating, the keynote from Andrew Ng, right? Kind of very non-traditional, right? He broke out the whiteboards, and I would recommend a lot of people to check out that, because I really felt that, of course, he is well respected and things like that, but the things that he highlighted, I really felt they really hit home Because of course, people give great keynotes, and I think they are good, but I think he really said these are the real things that you need to worry about or look at that are very relevant versus let's just try to increase the hype curve further and further, right? I thought that was very, that's something that I know I will kind of reference several times watching the video because he really brought some of the key points out there.
Awesome. Great. Well, thanks both of you.
Thank you for having us come.
Yeah, thank you. Long time listener and finally hearing my voice, it's going to be weird. So thank you so much for having us.
Awesome. Enjoy the rest of the conference.
Thank you.
All right, everyone. That's our show for today. Thanks so much for listening and, of course, for your ongoing feedback and support. For more information on Mo and Laura or any of the other topics covered in this episode, head on over to twimlai.com/talk/54. For the rest of this series, head over to twimlai.com/AISF2017. And please, please, please send us any questions or comments that you may have for us or our guests via Twitter @twimlai or @SamCharrington, or leave a comment on the show notes page. There are a ton of great conferences coming up through the end of the year. To stay up to date on which events we'll be attending, and hopefully to meet us there, check out our new events page at twimlai.com/events, TWIMLAI.com/events. Thanks again for listening, and catch you next time.